Something happened 15 billion miles from Earth, something that NASA's most experienced engineers did not predict, did not model, and cannot fully explain. Voyager 1, a spacecraft built with 1970s technology, running on less computing power than you. Our wristwatch, STADA, has sent back data from the deepest edge of known space that has quietly shaken the foundations of interstellar science. The readings don't match the models. The magnetic field shouldn't behave this way. The energy signatures weren't supposed to exist out there. And yet, they do. The question isn't whether something found Voyager 1. The question is, what found it first? There's a spacecraft out there right now, older than most of the people watching this video, traveling through territory that no machine built by human hands has ever crossed before. It weighs less than a small car. Its entire onboard computer, the one responsible for everything it tells us about interstellar space, operates on a memory bank of just 69.63 kilobytes. That is roughly the size of a single low-resolution thumbnail image. And yet, despite all of that, Voyager 1 continues to do something remarkable. It keeps sending signals back, faint ones, delayed by over 22 hours each way, but signals nonetheless. And what those signals have been saying recently has left some of the world's most seasoned space scientists sitting quietly at their desks, staring at data that refuses to make sense. Most people think of Voyager 1 as a relic, a feel-good story from the 1970s, a golden record and a pale blue dot, and Carl Sagan's poetic voice drifting through a documentary. That's the surface version, the one built for public consumption. But underneath that comfortable story, there is a scientific mission that has been producing genuinely unsettling discoveries for the past several years. Discoveries that quietly rewrite what we thought we understood about the structure of space beyond our solar system. And the deeper Voyager goes, the stranger the data becomes. To understand what is happening now, you need to understand where Voyager 1 actually is. As of mid-2025, the spacecraft sits approximately 167 astronomical units from Earth. That's 25 billion kilometers. To put that in perspective, Pluto, which already feels impossibly far, sits at roughly 40 astronomical units. Voyager 1 is more than 4 times farther than that. It crossed the heliopause, the official boundary between the sun's influence and true interstellar space, back in August 2012, becoming the first human-made object to physically leave our solar system. And in the 13 years since that crossing, it has been moving deeper into territory that our best theoretical models had only ever attempted to describe from a distance. What it has found out there does not match those descriptions. Not even close. Here's where the story starts to get complicated. When Voyager 1 crossed the heliopause in 2012, scientists expected to find a relatively calm and uniform interstellar medium on the other side. Cold plasma, steady magnetic fields, gradual cosmic ray intensity. The models were built on decades of theoretical physics and remote observation. They were confident. They were wrong. The interstellar magnetic field direction that Voyager 1 measured after the crossing was more than 40 degrees off from what every other observation method had predicted. Not slightly off, not within measurement error. 40 degrees? That is not a calibration issue. That is a fundamental misunderstanding of what the interstellar medium actually looks like up close. Scientists initially explained this as a distortion caused by the sun's influence bleeding across the heliopause boundary. But then the data kept coming, and with each year, the picture grew more complicated. In the year 2020, something changed. Voyager 1's magnetometer began registering an abrupt jump in the intensity of the magnetic fields embedded in the surrounding interstellar plasma. Simultaneously, its plasma detector measured a sudden rise in plasma density. These kinds of transient events had been observed before. Pressure surges, generated when massive eruptions from the sun slam into the heliopause and send shockwaves rippling outward into interstellar space, briefly compressing the surrounding plasma and intensifying local magnetic fields. Scientists understood that mechanism. They had seen it before. What they expected was that after a few months, the readings would return to baseline. That's what always happened. But this time, they didn't. The elevated magnetic field strength held. It didn't spike and fall. It stayed. And as months turned into years, the readings continued to reflect a sustained, unexplained elevation that refused to resolve. By 2024, Voyager 1's magnetometer was reporting magnetic field values consistently between 0.45 and 0.53 nanoteslas, elevated above what the models predicted for that region of interstellar space, and maintaining that elevation across an extended period that had no precedent in the mission's entire history. Think about what that means. A spacecraft in the middle of interstellar space, territory that was supposed to be the closest thing to empty that the universe offers, was sitting inside a persistent, elevated magnetic structure that wasn't supposed to be there. Some scientists proposed it was an enormous pressure wave, still propagating outward from intense solar activity. a slow-moving swell of compressed plasma drifting through interstellar space like a sound wave through still water. Others began suggesting something more unusual. That Voyager 1 may have drifted into what some researchers were calling a plasma cloud, a dense region of ionized gas expelled by a distant stellar explosion, potentially thousands of years old, drifting through the interstellar medium like a ghost of a dead star. Something left behind, something ancient, something that was already there long before our solar system had its current form. But here is where everything changed. In late 2084, Voyager 1's remaining instruments detected something that broke the pattern entirely. The spacecraft's sensors registered a sharp, sudden surge in high-energy particles, not the gradual increases associated with solar pressure waves, but a rapid, discontinuous spike consistent with a boundary encounter. Something like hitting a wall, except the wall wasn't supposed to be there. And almost immediately after that spike, the magnetic field direction shifted. Not gradually, as the 2015 study predicted it would, but quickly, inexplicably, as though the spacecraft had grazed against the edge of some structure that none of our models had placed at that location. Scientists noted it was as if Voyager 1 had skimmed against a boundary, or perhaps entered one, that no mission had ever detected from the inside. The interstellar medium, which was supposed to be an open, relatively featureless ocean of thin gas between the stars, apparently has internal architecture, layers, boundaries, structures that our instruments on Earth, no matter how sophisticated, simply cannot see from 25 billion kilometers away. Now layer on top of that another critical piece of context. Just weeks before those late 2024 readings arrived, Voyager 1 had already been through one of the most harrowing engineering crises of its entire 47-year mission. In November 2023, the spacecraft had suddenly begun transmitting complete nonsense, binary gibberish. The signal was reaching Earth, the hardware appeared to be functioning, but the data was unreadable. For months, engineers at NASA's Jet Propulsion Laboratory, some of them consulting retired engineers in their 80s who had originally built the spacecraft, worked to diagnose a fault in a machine so old that its operating documentation existed only on paper in archive storage. They eventually traced the problem to a corrupted chip inside the flight data subsystem, one of the most critical computers on board, responsible for packaging all of Voyager's science and engineering data before transmission. The chip held roughly 3% of the entire FDS memory. When it failed, whether from a cosmic ray strike or simple material decay after 46 years in the void, nobody can say with certainty. It took down the spacecraft's ability to communicate coherently. What followed was one of the most remarkable acts of remote engineering in human history. Working through a communication link with a 22.5-hour one-way delay, engineers broke the corrupted code into fragments, identified unused corners of the 69 kilobyte FDS memory where the pieces could be redistributed, rewrote each fragment so it would still function as part of the whole, and then beamed the repair patch across 24 billion kilometers of space. On April 20th, 2024, after months of silence, Voyager 1 started talking again. The conference room at JPL erupted, and within weeks, science data began flowing from 2 of the spacecraft's 4 remaining active instruments, including the magnetometer and plasma wave subsystem that would, just months later, begin returning those anomalous late 2024 readings about the unexpected magnetic boundary encounter. The data that has scientists quietly disturbed right now only exists because a small team of engineers managed to perform open-heart surgery on a computer smaller than your thumb from a quarter of the way to the nearest star with a 2-day turnaround on every command. And then, before that relief could settle, another crisis hit. In October 2024, Voyager 1's fault protection system activated unexpectedly, triggered after NASA engineers turned on one of the spacecraft's heaters. The system responded by lowering the transmission rate and eventually switching off the X-band radio transmitter that the spacecraft had been using to communicate with Earth since 1981. It automatically switched to the S-band transmitter, a backup radio that had last been used over 40 years ago. Engineers scrambled to find the signal on the new frequency. They succeeded. And in mid-November 2024, the X-band transmitter W has restored. 2 engineering crises in less than 12 months on a spacecraft that exists entirely as what engineers call single string, meaning every component has no backup, no redundancy, and 1 failure away from mission-ending loss of contact. All of this was happening simultaneously with the strange scientific data coming in. A spacecraft repeatedly stumbling through its own mechanical survival, while its surviving instruments were detecting an interstellar environment that defied decades of theoretical prediction. And here is the most unsettling part of that picture. As Voyager 1 was fighting for mechanical survival, it was also making those observations about the elevated sustained magnetic field structure, the structure that has, as of mid-2025, still not resolved back to baseline. Scientific analysis published in 2025 and extending through mid-2025 data confirms that the magnetic field environment in the region Voyager 1 is currently traversing remains, as the researchers put it, remarkably distinct from what was observed before 2020. The field strength hasn't fallen, the orientation continues to rotate in ways that suggest something is still influencing it, and the turbulence patterns in the surrounding plasma, while trending downward compared to the peak of the 2020 anomaly, still show transient spikes that have no fully agreed upon explanation. There are several theories on the table, and none of them are entirely comfortable. The first and most conservative is that Voyager 1 is traversing the extended aftermath of a series of powerful solar events, that the pressure waves generated by intense solar activity in previous years are still propagating through interstellar space, and that Voyager 1 has been sitting inside this compressed region for years. And this is scientifically plausible. The problem is that the duration and consistency of the elevated readings are stretching this explanation to its outer limits. Solar-generated pressure waves are transient. They move. They dissipate. This one has not. The second theory, and one that serious astrophysicists have been willing to discuss, is that Voyager 1 has entered a previously uncharted interstellar structure, possibly the remnant shockwave of an ancient stellar explosion, a filament of unusually dense magnetized plasma that drifts through the local interstellar medium on timescales measured in thousands of years. This theory would mean that the region of space our solar system occupies is not the featureless background medium that older models assumed, but rather a layered, textured environment with internal boundaries that only become visible when something physically passes through them. And then there's the third category of explanation, the one that scientists are careful to frame as speculative but have not been able to dismiss outright. The possibility that the structure Voyager 1 is encountering represents something that does not fit neatly into existing categories. The interstellar medium contains dark matter by every cosmological model we have. Dark matter interacts gravitationally and potentially through weak nuclear force, but its distribution is not uniform. There are regions of higher and lower density. Whether Voyager 1's instruments could even detect dark matter interaction is genuinely uncertain. Its sensors were not designed for that purpose. But the anomalous readings have opened a conversation at the fringes of the scientific community about whether our instruments are picking up the edges of something that our physics has not yet named. That is not a comfortable conversation. It is, however, a conversation that is happening. Meanwhile, the clock is running. Voyager 1's power supply is a radioisotope thermoelectric generator, a system that converts heat from the radioactive decay of plutonium into electricity. It has been losing roughly 4 watts of power every year since 1977. By early 2025, that attrition had become critical enough that NASA made the decision to power down Voyager 1's cosmic ray subsystem, the suite of 3 telescopes that had helped definitively confirm the spacecraft's crossing of the heliopause in 2012, on February 25, 2025. 3 science instruments remain active on Voyager 1 now: the magnetometer, the plasma wave subsystem, and the low-energy charged particle detector. The particle detector is scheduled for deactivation in 2026. After that, 2 instruments remain: the magnetometer and the plasma wave subsystem, the ones that are, not coincidentally, most directly measuring whatever it is that Voyager 1 is currently moving through. JPL engineers believe they can keep at least one of these running into the early 2030s. But they are also realistic. The spacecraft is 48 years old. Its circuits have absorbed decades of cosmic ray bombardment. Every day of continued operation is borrowed time. And there is one more complication that almost nobody outside the deep space operations community paid attention to. Between May 2025 and February 2026, Deep Space Station 43 in Canberra, Australia, the single most critical piece of ground infrastructure in the entire Voyager mission, and the only antenna on Earth powerful, enough to transmit commands to either Voyager spacecraft, went offline for major upgrades. For most of that window, the teams at JPL could receive data from Voyager 1, but sending new commands was nearly impossible. There were brief operational windows in August and December 2025, and teams scrambled to use them efficiently. In May 2025, just before the antenna went dark, engineers managed to revive a set of backup roll control thrusters aboard Voyager 1 that had been dormant since 2004, an act of preventive engineering carried out under a hard deadline, with no room for error, because the window to do it was closing. If those thrusters had not been revived in that narrow window, the spacecraft's ability to maintain its orientation, and therefore its communication link with Earth, could have been compromised at any point during the 9 months of limited uplink access. Read that again. The engineers who keep Voyager 1 alive are working within constraints so precise and so unforgiving that a 9-month antenna maintenance window becomes a mission-critical emergency that requires reviving 21-year-old dormant hardware on a deadline. What all of this adds up to is a picture that is far more dramatic and far more scientifically uncertain than the casual coverage of Voyager 1 suggests. This is not a museum piece coasting quietly through empty space. This is an active science mission, staffed by engineers consulting handwritten documentation from 5 decades ago, operating through a single ground antenna on the other side of the planet, communicating with a spacecraft that has survived 2 near-fatal technical failures in the past 2 years, while that spacecraft moves through a region of interstellar space that is behaving in ways our models explicitly did not predict. The region that Voyager 1 is currently traversing, what scientists are calling the very local interstellar medium, appears to be perturbed in a way that extends far beyond the heliopause boundary. It is not the pristine, undisturbed interstellar medium that theory suggested would exist at this distance. Something has structured it. Something has elevated its magnetic fields and sustained that elevation across years. Something generated that sharp particle spike and magnetic direction shift in late 2024. What that something is, the best scientists in the field will tell you plainly, is not yet fully understood. There's a line from Voyager's project scientist at JPL, Linda Spilker, that captures this entire situation with more honesty than most public announcements allow. Speaking about the nature of the Voyager mission in its current form, she said something to the effect of, "Every day could be our last, but that same day could also bring another interstellar revelation." That sentence is not poetry. It is an accurate operational description. Every morning that Voyager 1's signal arrives, it could be the last coherent transmission. And every transmission could contain data that forces a rewrite of our understanding of what lies between the stars. Both of those things are simultaneously true right now. That is the actual state of the farthest reaching mission in the history of human exploration. And what makes it more remarkable and more unsettling in equal measure is that we are not going to be able to simply wait for more data and build a clearer picture over time. The window is closing. In November 2026, Voyager 1 will become the first human-made object to reach a full light day from Earth. One light day, the distance light travels in 24 hours. It will be a milestone. And it will arrive during a period when the spacecraft is running on the power equivalent of a small nightlight, with 2 or 3 functioning instruments, monitored by a team small enough to fit in a conference room, through a command link that requires nearly a full day just for a signal to arrive. Whatever Voyager 1 discovers in the remaining years of its operation will be transmitted back across that incomprehensible distance in fragments, decoded by engineers working against the countdown of a failing power source, and interpreted by scientists who are increasingly confronted with the gap between what their models predicted and what the data is actually showing. The interstellar medium between the stars was supposed to be quiet. It was supposed to be the empty background of the cosmos, cold, thin, and largely featureless. What Voyager 1 has been finding since 2020, and what the late 2024 anomaly has intensified, is the growing evidence that it is none of those things. It is turbulent, it is structured, it has internal boundaries that we cannot see from here and could not have predicted without something physically crossing them. And we have exactly one instrument in the history of our civilization that has ever gone far enough to make those crossings, a 48-year-old spacecraft running on decaying plutonium and 69 kilobytes of memory, slowly dying in the dark, still talking to us, still sending back readings that refuse to conform to what we expected to find. What happens when it finally goes silent, when the signal stops and the data stops, and the only object humanity has ever sent beyond the solar system becomes permanently unreachable? We will be left with whatever it managed to transmit before the end. We will be left with the anomalous magnetic data that still hasn't been explained. We will be left with the record of a particle spike and a magnetic direction shift in late 2024 that suggests Voyager 1 encountered something, a structure, a boundary, a region of space with physics that doesn't match the textbook, and we will be left without the instruments to follow up on it. The next spacecraft capable of reaching interstellar space and making similar in situ measurements would require decades of travel time, even if we launched it tomorrow. And we haven't launched it. There is currently no approved funded interstellar probe mission on any space agency's active development schedule. Whatever Voyager 1 is finding right now, whatever it skimmed against in late 2024, we may not have another chance to investigate from the inside for 50 years, maybe longer. So when you hear that Voyager 1 may have made contact with an unknown force in deep space, resist the instinct to reduce that to a headline or dismiss it as speculation. The language of unknown force may be dramatic, but the underlying science is real, documented, and unresolved. Something out there in the very local interstellar medium has been holding a sustained elevated magnetic field for 5 years running. Something generated an anomalous boundary crossing signature in late 2024 at a location where no known structure was mapped. Something in the interstellar environment between the stars is more complex, more structured, and more active than any model built before Voyager 1 crossed the heliopause was able to predict. And the only machine we have ever sent to investigate it directly is aging, fading, and running out of time. The data it sends back now, fragile, delayed, from a computer smaller than your phone's cache, may be the last close-up view of that mystery that our civilization gets for a very long time. And what that data is saying right now in 2025 has not yet been fully understood by anyone on Earth. Not by the engineers, not by the astrophysicists, not by the mission scientists who have spent their careers on this. The answer to what Voyager 1 encountered is still out there, drifting in the dark, 25 billion kilometers from the nearest human being. And we are almost out of time to ask it,